In the last presentation, we talked about the concerns of AI, but in this presentation, I'll talk about more of the positive aspects of AI and how we can actually use AI for data privacy. So first, let's just talk about what is data privacy. So we want to secure all of this PII, or personally identifiable information, right? We don't want everyone in the world to know about our healthcare information, where we are. Right now, maybe we want to advertise that we're at this stadium, but I don't want everyone to know where I am every day. So we want to keep this information secure, and we want to ensure data privacy. Now, one issue with data privacy is that it's very easy to hack into these servers. So in traditional machine learning, we have one server typically. So in machine learning, usually it's just one server, and this one server has all of the data on it. So if you're a threat actor, you can just hack into one server, and you get access to all of the data. So that's an issue. In centralized machine learning, which is the traditional machine learning, we have one single point of failure. But is there a better way to harness the power of machine learning without having this single point of failure? And yes, there is. It's called federated learning. So federated learning is a machine learning technology that is basically a distributed version of machine learning. So in this system, we have a network of devices. So what that means is I have a network of all of these different mobile phones, and I'm going to send updates to a server, but I'm not sending the data on my phone. So we all have apps on our phone, right? We have Instagram, Facebook, maybe news apps, just random apps on our phone. And we don't want everyone to see the content of every single app. But we might want to make a better user experience. So in that case, our phone is going to say, I used these different apps today. I like these topics. And it sends that to the server. And then the server gets that information from my phone, but it also gets information from all of your phones, but it's not getting our data, it's just getting updates to a machine learning model. So for example, we've all heard of targeted advertisements, where social media applications use our location information to target us for certain ads. So in this case, let's just say all of us, we're in cybersecurity, so it might give us a lot of cybersecurity ads. So that's what the server is going to get. It's just trends in the data, but it doesn't actually get the data. So that's how federated learning works. So typically, to refine machine learning, we would do this process for several rounds, right? So if, for example, I'm on Instagram, and I am looking at one post about hacks and hops, and then all of you are looking at different posts about hacks and hops, then that's one round, and I select maybe this middle section over here in front of me, and we're all going to collaborate, and we're going to say that all of us like cybersecurity, and it does that for one round. And then it goes into this section over here, and it says, okay, what are your preferences? And then it looks at that and says, okay, you like cybersecurity too? That's another round. So it's averaging all of the information for all of us. So it's looking at all of us over here, all of us over here, all of us over here, just everyone in this area. And it's going to say, based on the averages that I see the trend of everyone really likes cybersecurity. So that's what I'm going to send to the application that is using federated learning. But federated learning is used in many different scenarios. While this might seem like a futuristic technology, it's actually being used in healthcare and in telecommunications. Basically, any kind of system where they have multiple devices and they all want to collaborate on something without sharing data. So this has actually been used in healthcare for COVID-19 research. So on the slide, you'll see there are 3 different hospitals, and they can all collaborate to learn about COVID-19. But they're not sending patient information when they are collaborating on this machine learning model. So it just says that based on the data that I have, I see this trend. So the server is going to say, what do you think the trend is for this COVID-19 research? And then hospital 1 would say, okay, I'm going to update the model that I actually think we see it more in older individuals, so it will send that to the server. And then hospital 2 will also do this at the same time and say, I see this trend with a certain demographic. And they keep doing this to just update the model itself, and the server is going to average all of these updates to say that I noticed COVID-19 is prevalent among people of a certain age group, of a certain demographic, of a certain location. But it doesn't have access to our healthcare information. It only has access to the trends that the hospital is telling it. So in this way, it is preserving patient privacy because they're not looking at the data itself. They're just looking at trends based on the selective information the hospital shares. Like, I see COVID-19 with older individuals, but it doesn't say that I see COVID-19 with patient A, B, or C. But can we actually make this better? Can we enhance federated learning? And the answer is yes. We can actually make this even more private and make the data even more private and more secure. So we can actually enhance federated learning and make it better by using something called privacy enhancing technologies, or PETs. So I'm going to talk about 3 different versions of privacy enhancing technologies, and these have actually been used to enhance federated learning in the industry. So the first privacy enhancing technology I'll talk about is secure multi-party computation. The second one is homomorphic encryption, and then the third one is differential privacy. So let's talk about the first one, secure multi-party computation. So in this type of privacy-enhancing technology, remember I said all of us are collaborating on the machine learning model. Now, let's just say we have a secret, and this secret is something we don't all want to know. Maybe the secret means the total trend of everyone in the stadium. Maybe I only know what's on my phone, for example. So in secure multi-party computation, we each have a part of the secret. So in this case, it would mean this section, for example, has access to the trends that they see, but they don't know what's happening in the other section over here. So we only see part of the secret. So here on the slide, you'll see that there's a party of people, and 3 of them are circled. So that means that 3 people each have a different part of the secret. So in this way, they can all come together and say, I have one part of the secret, and then only the server will know the true secret. They only know their part of the secret. So this is a way to a secret share and also to prevent the secret from being known by everyone. And now the second way we can actually enhance federated learning is by using homomorphic encryption. How many of you have already heard of homomorphic encryption? Show of hands. A few people. So this is typically a technology we hear about in research a lot. People keep talking about homomorphic encryption, that it's the next big thing in cryptography outside of post-quantum. And the idea of homomorphic encryption, it's actually very simple. So instead of computing everything just with raw data or raw information, I'm going to compute everything in an encrypted state. So what this means is if I'm the server and I'm receiving updates from each of these sections, I don't actually see the trends. Like, I don't see cybersecurity. I don't see hacks and hops. I don't see FR secure. I see just an encrypted ciphertext. So in homomorphic encryption, the server only has access to encrypted data. They don't have access to the raw data. So this is a way to make it even more secure. So in this case, each phone or each person would send the server encrypted information. And now you might be wondering, how does the server actually know, based on this encrypted information, what the model should be? Or what is the final result of all of the trends that we see? And the answer is they use homomorphic encryption to securely average all of these updates. So there's a lot of math involved, but the gist of it is we're using encryption so that no one can actually see the trends. So we don't have something like a man-in-the-middle attack where some random person in this stadium could see that we really like cybersecurity and hacks and hops, right? So we want to sometimes secure this information because we don't want everyone to see the traffic from our phones, and we don't want everyone to see the trends that we are giving to this server. So in this case, the server cannot figure out the model updates for each client, and that's because everything is encrypted. And now the last privacy-enhancing technology that we'll talk about is differential privacy. So differential privacy is actually something that we use in healthcare and in telecommunications. It's basically, we want to add noise itself to the model updates, to mask the model updates themselves. So in differential privacy, we are only going to have these updates, but they have noise added to them. So one challenge with this is in federated learning, when we have all these different clients giving us model updates and we use differential privacy, then we add this noise, but the challenge with adding the noise is that sometimes it can actually compromise the performance of the model itself. Because if we add too much noise to the model, then it impacts the performance. So in research, they have actually used differential privacy with federated learning to preserve the privacy of the model and to try to make it more private. But the challenge we see in a real-world scenario is that if you use differential privacy, for example, with all of us here, and we try to send the model updates to the server, if this was an ideal scenario, what's going to happen is we all have these differentially private model updates, which means that cybersecurity, hacks and hops, that trend, we're going to add noise to it. So instead of saying cybersecurity, it might say something else completely different. And then the server will use math to determine what actually the updates are. But the challenge is if we transform cybersecurity to something like soccer, and the server receives some cybersecurity instead of cybersecurity, we say cybersecurity is not the trend we see soccer. And then we give this to the server might be able to create this and say cybersecurity is the trend, but let's say we're an end user and we use this model, that's going to be a challenge, because if we ask the end user what is the trend we see, and the model responds with soccer, then it's really difficult to decide or determine what the real trend is, because we see soccer instead of cybersecurity. So that's a challenge we have in the real world scenario, is that when we add differential privacy, it's actually very difficult for us to add, to have a model that's not only private but also accurate. However, this has been used to enhance healthcare. So in a lot of healthcare applications where they don't have an end user and it's all internal to the system, then they use differential privacy. And in this case, it does work because an end user is not seeing the output of the model. So for example, a hospital, they don't see what is inside the hospital database, right? We only see our patient records. But in that case, they use differential privacy. And so to enhance federated learning, we want to combine all of these different privacy-enhancing technologies. So I know there's a lot of fear about machine learning and about privacy and data privacy, but there is actually a lot of research happening to ensure that we can harness the power of machine learning while also preserving data privacy. So if you wanted to implement federated learning in your own organizations, it's actually very easy to do so. So there are a lot of different systems and tools that you can use to adopt federated learning in your own systems. So the ones I've listed here are open source, which means they're available to everyone. And federated learning is just a type of machine learning. So in your organizations, if you have data scientists or you have developers, they can easily implement federated learning in your organizations. It's typically implemented with Python. So in federated learning, we typically use Python, which is a standard language for machine learning. And then you can use PySwift or Flower or TensorFlow or many of the other tools out there to implement federated learning. So the idea is that just if you have machine learning or AI already in your organizations, it's very easy for you to tack on federated learning to it. So it just enhances data privacy for you, and it's very useful in industries where we want to ensure that there is data privacy, healthcare, telecommunications, government systems. So it's a really useful technology. And so I wouldn't be scared of federated learning or AI or machine learning. It's actually very useful. In fact, it's coming out in a lot of different applications now. So that concludes my presentation. Please feel free to contact me. You can either use LinkedIn or you can email me directly. My email is just anmol@aloratech.com. So just my first name @aloratech.com. Thank you so much.